All right, welcome to the next video. We are going to be talking about periodic trends today. Okay, so this is still Unit 1, Atomic Structure and Properties, Topic 7, Periodic Trends. The learning objective for this topic is for you to be able to explain the relationship between trends in atomic properties of elements and their electronic structure and periodicity. Okay, we are going to be getting into Coulomb's law again. But first, we're going to take a look at some terms that I think need some better defining. Okay, we've sort of touched on these terms, nuclear charge and electron shielding, as well as valence and core electrons. So we're going to have a little bit of a discussion of these two things. We're going to sort of wrap this up into Coulomb's law. Okay, so we're going to revisit that again. And then we're going to apply Coulomb's law to help us understand periodic trends. Okay, so that'll be the main purpose for this video. And then in the second video, I'll do some example problems showing you how to basically apply what we learn here in the periodic trends to some different groups of elements. Okay? All right, so like I said, let's define a few terms that we've sort of thrown around a little bit. Let's try to really nail down what these terms mean, okay, so that we can use them productively in our class. Okay, nuclear charge is the charge of the nucleus. Duh, okay? We're going to use this, use the variable z to represent the nuclear charge in an atom, okay? Z is equal to the number of protons, okay? So for our purposes right now, if we're talking about, say, this element right here, this guy looks like it has 7 protons, so we would say that Z is equal to 7, okay, or positive 7, right, because this is a positively charged protons here, so positively charged nucleus. So that's what the nuclear charge is, okay, represented by the variable Z. The effective nuclear charge, and we're really going to be talking about this a lot today. Okay, I think this is a good and useful term to talk about. The effective nuclear charge is something different. Okay, electrons, depending on their location and the presence of other electrons, will almost never feel the entire attractive force of the nucleus's pull. Okay, so let's say you're this electron here, right? The electron of interest. You are going to feel an attractive force from the positively charged nucleus. However, due to the fact that there may be other electrons in between you and the nucleus, you're not going to feel the entire attractive force of the nucleus's pull. Or, well, you will feel the entire force, but it's going to be canceled out somewhat by the presence of these other electrons. Okay? So, in fact, after I record this video, I'm going to go back and rephrase this a little bit because this is not the best way to phrase this. And you'll see a little bit further down the line how I actually want you to phrase this when we talk about effective nuclear charge. Okay, let's also talk about the difference between valence and core electrons. Okay, so we're going to come back to effective nuclear charge in just a second. Valence electrons, I think a lot of you have heard this term before already and sort of know what this is. Valence electrons are the electrons in the outermost energy level of an atom. Okay, so in this little diagram or this little drawing here, we would say that these 5 electrons in nitrogen, these 5 electrons on the outside, those would be valence electrons. Okay, core electrons are all the other electrons. Okay, so they're the innermost electrons or the inner electrons in an atom. Electrons are either valence electrons or core electrons. Okay. So the core electrons for nitrogen here are just the 2 that exist in that first energy level. If you look at the electron configuration for nitrogen, you can figure out where these electrons are, right? So the core electrons are the electrons in that 1s orbital, while the valence electrons are the electrons in the 2s and 2p orbitals, 2 plus 3 equals 5, right? So those 5 out there. Okay, so let's get back to talking about effective nuclear charge. Okay, now that we have some vocabulary to use. Okay, so the positive charge in the nucleus is going to attract electrons. Okay, however, core electrons are going to repel these outer electrons as well. Okay, So you can see here in this diagram, let's imagine we are this outer electron, or this one, okay? We feel an attractive force towards the nucleus, but we also feel and exert a repulsion from this electron, and this one over here too, okay? Even though that's not drawn, there is still a repulsion going on between this one and this one. So this is what we talk about, or this is what we mean when we talk about the effective nuclear charge, okay? Just the nuclear charge is the value of Z, right? The magnitude of the number of protons in the nucleus. But the effective nuclear charge, what the proton or what the electron here effectively feels, is somewhat negated by the presence of these core electrons. Okay? And there's actually a bit of an equation that we're going to kind of use that's a bit of an approximation for calculating the effective nuclear charge. It's pretty simple. So Z is the number of protons, right? So the effective nuclear charge is equal to Z, the number of protons, minus S, where S is some shielding factor, okay? So you can see here that the effective nuclear charge is always going to be less than or equal to Z, right? If the shielding factor is 0, right, so let's say an atom of hydrogen, right, where there are no core electrons in our way, then the effective nuclear charge would be the exactly the same as the nuclear charge. But for bigger elements, right, so think lithium and onwards, there is going to be some shielding factor, okay? And we can kind of think as S as just being the number of shielding electrons. That gets a little bit messy, okay? It's definitely an approximation, but it can kind of help us grapple with this idea of effective nuclear charge, okay? So I want to talk a little bit about this term, okay? Electron shielding, because I've just talked about like a shielding factor, okay? And you're going to see this concept pop up whenever we discuss, or whenever you see things like periodic trends being talked about, okay? Whether it's in a textbook or online or even on an assessment, okay? So this phenomenon that I've just sort of described, right, the repellent effects of these core electrons, this phenomenon is sometimes referred to as electron shielding. Okay? The core electrons, in effect, act as a shield due to their repellent effect. Okay? And keep in mind, we are this outer electron, right? So these core electrons are kind of acting like a shield, protecting us, I guess, from the positive attractive force of the nucleus, right? Shields like protect things, right? You have to be really, really careful, and I have to be really, really careful, okay, in the way that we talk about these things. The valence electrons still feel the full attractive force from the nucleus, okay? However, the overall force felt by the valence electrons is somewhat smaller due to the repellent force of the core electrons, okay? It would be incorrect, let me go here. It would be incorrect to say that core electrons shield valence electrons from feeling the full attractive force of the nucleus. That would be incorrect. If you are this electron right here, you still feel the full attractive force of the nucleus. It's just that in addition to that attractive force, you are also feeling a repulsion, okay? So it's literally pluses and minuses, right? So you're feeling a positive force, or a positive, you're feeling an attraction, right, towards the nucleus, but you're also feeling a repulsion that's pushing you away. That's what this equation here is kind of talking about, right? The overall nuclear charge, or the effective nuclear charge, it is a function of how big the positive charge is, right, and how many repelling electrons you have in your way that are pushing you away. Okay. Hope that makes sense a little bit. I just want to be careful. I'm not a huge fan of this term electron shielding. I would rather us talk about it in terms of attraction and repulsion and how they can sort of counteract each other. I think that's sort of a better way of talking about things. Okay, so let's sort of tie this up then in in Coulomb's law. We talked about Coulomb's law a little bit last time when Mr. Alcampora was here, and a lot of you all were expressing some concern that you were still a little bit confused about what was going on. So I want to just briefly bring this back into our discussion here. So here's Coulomb's law. We're not really going to have to use the equation in terms of plugging in numbers, at least not right now. But we do need to understand what this tells us about how forces interact, okay? And actually, this equation down, I'm sort of covering it up there with the, okay, so the equation at the bottom of the screen, down there, that's actually the equation for the energy between two charged particles. Mr. Alcampora thought it was important that we know the difference between this equation here, which has r squared, and the equation down at the bottom, which just has r. Sorry, I've covered it up again. There is a difference in terms of, for this class, which one to think about. I think they both kind of tell us the same thing, okay? When the effective nuclear charge in an atom is larger, right? So let's say that that's Q1. Okay, so Q represents charges, right? Q1 and Q2 are charges. When the effective nuclear charge is larger in an atom, the magnitude of the attraction on an electron, okay, which might be Q2, is also going to be larger. Okay, and let's make sure we understand why, right? Q1 and Q2 are in the numerator of this expression here, okay? So the magnitude or the value of F is going to increase when Q1 increases. Okay, so if the effective nuclear charge is bigger than the force of attraction on the other charge, okay, because our electron, the charge of our electron is always going to be the same, right? Like the charge of the electron. One electron here is the same as one electron over here is the same as one electron over here. Okay, so like all the electrons that exist in the universe have the same numerical value in terms of their charge. Okay, it's this nuclear charge, or the effective nuclear charge, that can change from like atom to atom. Okay, so once again, as Q1 increases, F is going to increase. Okay, the opposite is the truth, or is the fact, when the radius or the distance increases. One other thing that Mr. A wanted me to tell you guys is that sometimes, and he actually prefers this, we should use D instead of R. So in fact, it says here R is equal to distance of separation. Well, why not just use the letter D, right? So this means like the distance between the nucleus and the electron that you're talking about. So it doesn't really matter, but all you really need to know, right, is that as the distance between the nucleus and the electron increases, right, so as you get further and further away from the nucleus, this term down here in the denominator gets bigger, which means that you're overall dividing by a bigger number, which means the force actually goes down, right? So as the effective nuclear charge increases, F increases. As the distance between the particles, or as your distance from the nucleus increases, F decreases. Okay, and that would be the exact same for the energy, okay? Because once again, Q1 is in the numerator and R or D is in the denominator, okay? Okay, so what we're going to do then today is we're going to talk about periodic trends, but we're going to be using Coulomb's law and our knowledge of like effective nuclear charge to help us understand why these trends are the way that they are, okay? So due to the periodic nature of the periodic table, as determined by the atomic structure of the elements, the electron configurations essentially, remember that the shape of the periodic table is the way it is because of the electron configurations inside of atoms, right, where those electrons are. There exist general trends of properties which we can discover, okay? We're going to talk about a few different trends today. The first one we're going to talk about is for effective nuclear charge itself, okay? So we're going to take a look at the periodic table and we're going to try to talk about, generally speaking, how does the effective nuclear charge change as you go across a period, so from left to right, and then how does it change as you go down a group? Okay, so we're always going to talk about the trends, the period trend as going from left to right, and we're going to talk about the trend, the group trend as you go from top to bottom. Now you could talk about it in reverse. Okay, it doesn't really matter, but for the purposes of this video, I'm going to talk about it in that way. Okay. All right. So here is a nice little chart diagram thing that I created several years ago. I only have a picture of it. I don't have the actual piece of paper anymore, so I'm stuck using the picture. This is a diagram that shows Bohr models of lots of different elements. Okay, so many different elements in the first 4 rows on the periodic table. Something to note here is that I have not drawn any of the transition metals. Okay, so these are actually the group A elements, group 1, 2, 3, 4, 5, 6, 7, and 8A. You'll sometimes see them referred to as group A elements. Basically, it's the 2 sides of the periodic table. The first 2 columns over here, and then the last 6 columns over here. The S block and the P block. Okay, these would be the S block elements. These over here would be the P block elements. Okay, so let's see if we can answer this first question. How does effective nuclear charge change as you go across a period on the periodic table? Okay, the one downside of what I've drawn here is that we don't actually get to see the number of protons. But I think a lot of you all are smart enough and can recall sort of the atomic numbers of these elements. Lithium is number 3, beryllium is number 4, boron is 5, and so on. Okay, so 5, 6, 7, 8, 9, 10. As we go from left to right across the periodic table, the nuclear charge is increasing, right? Remember, the nuclear charge is just the number of protons. So that is clearly increasing, right? From 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10. What we're concerned with, though, is the effective nuclear charge, okay? So we have to imagine ourselves as being one of these electrons and trying to predict what kind of attractive force these electrons are feeling, okay? How much attractive force are they feeling? Is the attractive force that they are feeling going up as we go across this table, or is it going down, or is it staying the same, right? And we have to think back to Coulomb's law, okay? So we just said, right, that the nuclear charge is increasing, right? So the number of protons is going up, all right? Is the distance increasing? Are the valence electrons getting further and further away as we go across? They don't appear to be, right? They're all being added to this second energy level. And granted, those would technically be different orbitals, right? Here it would be the 2s orbital, and then here it would be the 2p orbital. But in terms of the distance from the nucleus, the reason that this is a good approximation, drawing a model like this, is because those electrons are roughly the same distance away, okay? Now, as you go down a column, that's a different story. But as you go across a period, adding electrons to the same valence level, right, so the second level here being the valence level, you're not really increasing the distance from the nucleus when you do that, okay? In fact, as we'll see later, it's the opposite. So, we've got an increasing number of protons, and our distance is not increasing, okay? So our nuclear charge is increasing, and our distance is not changing, okay? What that means then, right, is that the force of attraction being felt by those protons is increasing, okay? So the effective nuclear charge as you're going across, right, the effective nuclear charge, if I go back to this diagram here, the effective nuclear charge is the sort of, it's a measure, right, of like the amount of force that these electrons are feeling. It's going up, right? And it's going up because the number of protons is increasing. There's no other factor here that's really changing that very much. Now there is another thing that I do want to talk about, and that is the fact that as you're adding electrons here, you're adding electrons to energy levels, or to orbitals more specifically, that already have electrons. So there is something of a repulsion effect that does occur in that situation. It's something that you really have to look at like a case-by-case basis, though. Okay, so we're trying to talk about just sort of the general trend on the periodic table right now. So the general trend, once again, is that as you go from left to right, the number of protons is increasing, the distance isn't really changing, and so the overall effective nuclear force is increasing. Okay, and once again, just to bring things back to this equation, if we really just think of it in terms of this equation, right? Let's say S is just the number of shielding electrons, right? Check this out. The effective nuclear force is equal to the number of protons minus the shielding electrons. Well, here I have 3 protons minus 2 shielding electrons, so that would be an effective nuclear charge of 1. Here I have 4 protons minus 2 shielding electrons, so an effective nuclear force of 2, and then it goes up, it increases in that way, 1, 2, 3, 4, 5, 6, 7, 8, and so forth. Okay, so there's a couple of different ways you can think about it, but regardless of how you think about it, you arrive at the same conclusion, and that is that the effective nuclear charge clearly increases as you go from left to right across a period. Okay, definitely increases. The nuclear charge increases while the shielding factor remains roughly the same. Okay. Now the group trend is a bit more complicated. Okay, and I'm not going to try to walk us through the nitty-gritty details of the group trend. I don't think it's that important in comparison to the period trend here. All I'll say is that the effective nuclear charge does increase as you go down a column. If you use this little approximation equation here, it looks like the effective charge doesn't change at all, but in reality it does actually increase. And this is because the valence electrons in larger atoms generally experience weaker shielding effects than valence electrons in smaller atoms. Okay, so like this valence electron in potassium, the shielding that it experiences from these core electrons is a bit weaker in strength than the shielding that the valence electron in lithium experiences from these core electrons. Okay, that's a really sort of fine-grained detail that I don't want you to worry about too much. But the effective nuclear charge does increase as you go down a column. Okay. All right, we're going to talk about two other periodic trends in this video. We're going to talk about ionization energy and atomic radius. I am not going to discuss electron affinity. There is a section in the book that talks about electron affinity, and there are some questions in the problem set for this this topic that ask you about electron affinity. Okay, so I'm going to be talking about ionization energy, which is somewhat similar to electron affinity. And when you answer the questions on electron affinity, I want you to be thinking about the same sorts of things that we're talking about when we talk about ionization energy and atomic radius. Okay, it all boils down to effective nuclear charge, shielding, Coulomb's law. Okay, so the fact that I'm not talking about electron affinity in specific details here in the video does not mean you can't grapple with it as a student. Okay, so this slide is actually the same thing that we looked at in the previous video. We did talk about ionization energy. Ionization energy is the energy required to remove an electron from an atom. Okay, it can be expressed like this little equation here. So you have some atom or some element X, and you're taking an electron away. So you end up with a positively charged ion of that element. So what we want to talk about today is how would ionization energy change as you go across a period on the periodic table and then down a group, right? And more specifically, how can we explain the trend, right? How could we determine or derive the trend based on what we know about effective nuclear charge, electron shielding effects, and like the distance that electrons are from the nucleus. Okay, so let's tackle this first question. How would ionization energy change as you go across a period? Well, let's focus on period 2 once again. Okay, so we've already determined, right, that the effective nuclear charge is increasing as I go from left to right. Right, the effective nuclear charge of fluorine is bigger than it is in oxygen, which is bigger than it is in nitrogen, etc. So we need to think about how does that apply to the energy required to remove an electron from that atom or from that element. So let's take two elements, okay? Let's take two that are at the opposite ends here of the spectrum, okay? So we can talk about neon and lithium, or we could talk about fluorine and beryllium. Let's do that, right? Let's talk about fluorine and beryllium. Okay, so the electron that's being removed, right? So the ionization energy, you can talk about the first ionization energy or the second ionization energy or the third. That's like the first electron being removed, second electron being removed, etc. Whenever we talk about like the trend of ionization energy, we're usually talking about the first ionization energy, okay? So we're talking about removing just one electron, and when we talk about removing the first electron, it's going to be one of these valence electrons, okay? All right, so let's try to compare situations here. All right, so for beryllium, we've got 4 protons here. We calculated, right, pseudo-calculated, our effective nuclear charge would be 4 protons minus 2 shielding electrons, so our effective nuclear charge here was 2. Our effective nuclear charge over here in fluorine was quite a bit bigger, right? 9 protons minus these 2 green shielding electrons, so effective nuclear charge of 7. And so what we said then was that the effective nuclear charge, right, is much bigger in fluorine, and that means that these valence electrons are feeling a stronger attraction towards the nucleus than the electrons in beryllium are, right? Think about just the magnitude of the positive charge, right? We've got 4 protons here compared to just 9. Or sorry, we've got 9 protons here compared to just 4, right? This is bigger. So, and we don't have any additional shielding effects, right? The shielding in beryllium is like the same as it is in fluorine. So what that means then is that for any one of these electrons here, it's going to be much harder to rip this electron away than it would be to rip it away from beryllium, right? The attractive force on each of these electrons in fluorine is larger than the attractive force on these electrons in beryllium, the valence electrons, okay? So because that attractive force is larger, stronger, the ionization energy, right, the amount of energy you would have to spend to rip that electron away, that is also higher, right? It's literally going to cost you more energy. You're going to have to do more work to take that electron away from fluorine than you would from beryllium, okay? So here that is just sort of written out. Ionization energy increases as you go from left to right across a period. Both the nuclear charge and the effective nuclear charge increase, right? So the number of protons and then the effective nuclear charge both increase as you go from left to right, while the valence level remains the same, right? We're not getting any further away from the nucleus, right? So this electron is the same distance from the nucleus, or roughly the same distance as this electron is. As you move from left to right, the electrons are more strongly bound, right, due to this larger effective nuclear charge. They're more strongly bound to the nucleus and thus require more energy to remove. Okay? So that's the period trend. And I've kind of spoiled things. You can see what the group trend is here. But let's try to talk about it. Okay? So as you go down a group, the effective nuclear charge does increase. Okay? So the effective nuclear charge increases as you go across a period, and it increases as you go down a group. The thing is, okay, even though the effective nuclear charge is increasing as you go down, what's also increasing is your distance from the nucleus, okay? And so if we look at our Coulomb's law equation, right, if our distance from the nucleus is increasing, then the attractive force goes down, right? And it goes way down, right? Because in this force equation, it's a square law, and in the energy equation, it's just divided by the distance. But in both cases, right, as the distance increases, the force or the energy goes down, okay? And so as you go down the column here, let's compare like potassium and lithium, for example. This valence electron in potassium, it is so much further away, right? And these are not necessarily drawn to scale, okay? It is so much farther away than the electron here that in effect the force that it's feeling is way smaller, okay? So it is actually way easier to rip this electron away from potassium than it is from lithium, okay? And there's that shielding aspect that's going on here too, right? But that's sort of wrapped into the effective nuclear charge. Okay, so what do I say about that? While the effective nuclear charge does increase, the valence level increases as well, right? You're going from the second level to the third to the fourth. The distance from the nucleus becomes the more dominant factor. The electrons are less strongly bound to the nucleus and thus require less energy to remove, okay? All right, and then the last section of the video here, sorry, this is a bit of a long one, is the atomic radius, okay? So let's talk about what the atomic radius is in the first place. So measuring the size of an atom, as you can imagine, can be tricky, okay? You can't just pull out your ruler, okay? Atoms are pretty small, so you can't just pull out your ruler and take a measurement. Now, it's funny because actually that is kind of what we do, except it's not with a ruler, obviously. So as we learned previously, the sizes of electron orbitals, right, because that would sort of determine the size of an atom, right? You've got the nucleus in the center, and then the electrons that exist in these orbitals outside of the nucleus, right? So we're trying to sort of visualize, like, where's the boundary of those orbitals. And that's a really hard thing to do. Those orbitals are just approximations, right, that are based on these probability distributions that we talked about before, right, getting back into all the quantum business. So you can't really just look at one atom and say, oh, I know exactly how big you are. It doesn't really work like that. What scientists have done instead is they look at substances, right? So either a metal or some sort of covalently bonded substance or some sort of ionic substance that involves multiple atoms together. And if you measure the distance between those two atoms and then have that, right? So measure the distance between the two atoms and then divide that by 2, that will effectively give you the radius, okay? So in a metal, if you measure the distance between two atoms in a metal, take the difference, or divide that distance by 2, that'll be your radius, right? And then the same thing in a covalently bonded compound. An example here would be like O2, right, oxygen gas, or an N2, nitrogen gas. Measure the distance between the nuclei of the two atoms, divide that by 2, and that will give you the radius of one of the atoms. And then it gets a little bit more complicated with ionic radius. We're not going to get into the details of this right this moment, but you effectively can do the same thing, even when it's atoms that are two different elements. It's a little bit trickier. You kind of have to use some information that you gained somewhere else to really get to the answer here. I think we'll probably end up doing this at some point, just not right this moment. What we need to talk about, though, today, and like I said, I am trying to wrap things up here, is the atomic radius trend, or the atomic radii trend, right? How would atomic radii change as you go across a period and down a group, right? And we want to try to explain this in terms of nuclear charge, shielding, distance from the nucleus, right? Coulomb's law, right? We want to try to explain the trend in terms of those things. It's not good enough in AP Chemistry to just reference the trend, right? Well, I know this one's bigger than this one because of the trend. You can't say that. That's not going to get you points or get you credit on the AP Chemistry exam. You've got to be able to explain things from the principles, right, from the nuclear charge, Coulomb's law, distance, from those sorts of arguments, okay? All right, so let's try to think of this in terms of the effective nuclear charge, right? What happens to the effective nuclear charge as you go from left to right? Well, as you go from left to right, effective nuclear charge increases, right? Due to that increasing number of protons and the same valence level. Okay? So, if the effective nuclear charge is increasing as you go from left to right, how would that affect the electrons that surround that nucleus, right? If the effective nuclear charge is going up, then how would that affect the electrons? Okay? Let's try to answer this question, right? As you go from left to right, would the electrons feel a stronger or weaker force of attraction? Well, if the effective nuclear charge is going up, you would feel a stronger force, right? Think about Coulomb's law, right? If Q1 is going up, then the attractive force is going up. So if the electrons are feeling a stronger force of attraction, how would that affect their distance from the nucleus? Would they be closer or farther away if they feel a stronger force? I hope you're thinking that they would be closer, right? And that's true, right? So this is kind of weird. This is one of the trends that people sort of, it's a little counterintuitive, right? Because so what the fact is that as as you go from left to right across the period, atomic radii actually decrease, okay? So even though we're adding more electrons and there's more protons in the nucleus, right? So like the mass of the atom is increasing, right? And the number of particles in the atom is increasing, the actual size of the atom is decreasing, okay? And that is a counterintuitive thing. So let's read the explanation here. It says, the explanation for this is similar to the explanation for the ionization energy. And in fact, all of the trends seem to have sort of very similar explanations, right? It really does all boil down to like nuclear charge, distance from the nucleus, Coulomb's law, those sorts of things. So both the nuclear charge and effective nuclear charge are increasing as you go from left to right. The valence level is remaining the same. And so as you move from left to right, the electrons feel a stronger force of attraction from the nucleus, and therefore can be found closer to the nucleus, right? If you feel a strong, it's not like they, the electrons aren't sitting there thinking about it, right? It's not like a conscious decision, but because they are feeling a stronger force of attraction, they just are closer to the nucleus, okay? And then for the group trend, this one is the easy one, okay? As you go down the periodic table, right, from top to bottom, atomic radii is obviously increasing, okay? This is because the atoms are just simply growing in size due to the additional energy levels of orbitals and electrons that can be found, right? If we go and take a look at our picture here, as we go from hydrogen to lithium to sodium, potassium, we're adding more electrons, and it's not just that we're adding more electrons, but those electrons, they are in increasingly larger orbitals, and so they're just further and further away, right? There's just not enough room to cram all those electrons into the same spot. We sort of learned that when we were talking about electron configuration. So the group trend is an easy one to remember, right? As you go down, atoms get bigger. Okay, I believe that's it for the video. So there will be a problem-solving video where like I said, what we're going to do is we're going to look at some different sets of elements and try to predict like which elements would be smaller, which ones would be larger, which ones would have higher ionization energies, which ones would have lower ionization energies, that sort of thing. And like I mentioned before, with electron affinity, there is a section in your book that talks about what electron affinity is. I'm expecting you to read through that section of the book, use what we've learned in this video, about effective nuclear charge, Coulomb's law, to be able to grapple with electron affinity and its trend on your own. Okay? Thanks a lot for watching, and I'll see you next time.